Hey everyone. Let me see now. Over the last couple of lectures, we were discussing this concept of spanning set. And I think I said something like, in terms of linear algebra terms, span, this idea of spanning sets, is in the top 5 in terms of important concepts. The next definition that I'm going to write down is in that category too. Absolutely, most definitely in the top 5 in terms of important concepts when it comes to linear algebra. So here we go. So let's say a set of vectors v1 up through v sub k in a vector space capital V is linearly independent. So we're defining this term linearly independent if the only solution to the equation a1 v1 plus a2 v2 plus dot 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 plus a sub k times v sub k equals the zero vector is the trivial solution a1 equals a2 equals dot 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 equals ak equals 0. And I should underline this word, or double underline this word only. Okay? So if you have an equation of this form right here, there is absolutely, most definitely, at least one solution. We call that the trivial solution, right? When all the ai's are equal to 0, the left-hand side will give us the 0 vector that's equal to the right-hand side. So in the case that our collection of vectors has only the trivial solution to this equation, then we say that the set is linearly independent. If not, right, if there is at least one non-trivial solution, which means that there's at least one AI that's not equal to 0, then we call it the non-trivial solution. In that case, so we'll say otherwise, the set is linearly dependent. Okay, so this is one of the big concepts, one of the big definitions from linear algebra. We want to understand this notion of linearly independence versus linearly linear dependence. Okay? Okay, so now let's look at some examples of this idea of linear independence versus dependence. So as a first example, in R3, I think I want to do, yeah, so let's look at R3. The set of vectors, so it's going to be 1, 0, 0, 1, 1, 0, and 1, 1, 1. Right, so here's a collection of vectors sitting in R3. There's nothing special about the fact that I chose 3 vectors here. It has nothing to do with this 3 right here. I just happen to choose 3 vectors. So this set right here is linearly independent. Now, the reason, right, so why is that? Well, so we need to appeal to the definition right here. If I look at this equation, so let's write a1 times the first vector. Oops. So a1 times 1, 0, 0 plus a2 times 1, 1, 0 plus a3 times 1, 1, 1, and we set it equal to the 0 vector. So that's the setup when you want to think about or or answer the question as whether your set is linearly independent or not. To use the definition, we look at this right here, this equation. And we ask ourselves, all right, what possible solutions do we have? What choices for A1, A2, and A3 are there? Well, if you look at the bottom, I'll call it the bottom row, notice what we would have in this equation right here, in the bottom portion, we'd have an A3 has to equal 0. All right, so from that bottom row, A3 has to equal 0. So if A3 has to equal 0, then this vector right there is not even in the computation. And now look at the second row. So we're going to have A1 times the first vector plus A2 times the second vector. That tells us, if you look at the middle row, that A2 has to equal 0. All right, so now that one's gone. All right, so we would just have A1 times this vector 1, 0, 0 has to equal 0, 0, 0, and that tells us then that A1 has to equal 0 also. That's the only solution to this equation. That tells us then that this set right here that we started off with is linearly independent. The only solution is the trivial solution. I'm going to do lots more examples. I should point out the definition that I just wrote down here does not match the definition given in the book. All right? The book gives a different definition of linear independence. I prefer to define it this way, and what we'll see in a little while is what I'm going to write down will match what the book says, right? And we'll see why, or talk about the connection between my definition and the book's definition as we go on. Okay, so next example. The set, well, it's in R4, so in R4, the set of vectors, so now we're going to have 1, 1, 0, 0, 0, 0, 1, 1, and 2, 2, 3, 3 is linearly dependent. And so let's see why that's true. So reason. Okay, so now what I'm going to do to show that it's linearly dependent, I'm going to show a non-trivial solution to the equation. So if you look at 2 times 1, 1, 0, 0 plus 3 times 0, 0, 1, 1 plus negative 1 times 2, 2, 3, 3, that equals the 0 vector. So what I've done here, I have produced a non-trivial solution to this equation right here. That's exactly what it means. If a non-trivial solution exists, then the system, or the set, is linearly dependent. Okay, let's move on to a different vector space. So now let's look at P2. So the set consisting of the vectors polynomials 1 plus x and x plus x squared is linearly independent in this case we're working in the vector space P sub 2. Remember, that's the set of all polynomials of degree less than or equal to 2. All right, to show that it's linearly independent, I need to show that the only solution to the equation is the trivial equation. Sorry, trivial solution. So, let's say the reason. So let's consider the equation. So it's going to be constant times the first vector plus constant times the second vector equals the 0 vector. So in this case, we have A. I'm going to just use A and B rather than A1 and A2. A times 1 plus x plus b times x plus x squared equal to 0. Right? This is the 0 vector when you're working in P2. Okay, so we consider this equation right here. And let's see, what do I get? I get A plus B times x plus b times x squared has to equal 0. Just lost my shoe there. What I just did is I just multiplied the things out and I joined the degree 0 terms, the degree 1 terms, the degree 2 terms together. Now, for this left-hand side to equal the 0 polynomial, I will need a equal to 0. I will need a plus b equal to 0, and I will need b equal to 0. Right? This forces. Right? The only way for this to happen, I will need a equal to 0 because there's no constant term, or the constant term over here is 0. There's no degree 1 term, so I need a plus b equal to 0. Doesn't really matter. I also need b equal to 0 because there's no degree 2 term. So because we are forced to have a and b equal to 0, the only solution is the trivial solution, which means that we've got a linearly independent set. A couple more examples here. So let's see. In Rn, the set consisting of E1, E2, all the way up to En is linearly independent. And I'm not going to work this out. I want you to work this out for yourself. It's fairly easy to verify. Another example, and these are facts that we'll need later on, in Pn, the set of polynomials 1x, x squared, all the way up to xn. This set right here is linearly independent. Once again, I'd like you to go through and verify that this set right here is linearly independent. A few observations. The first one, any set that contains the 0 vector is linearly dependent. Okay. It should be fairly obvious if you actually just write down, take a set, right, v1, v2, v3, and so on, and then throw the 0 vector in there. You'll easily be able to write down a non-trivial solution to the equation. If v is not equal to the 0 vector, then the set consisting just of v is linearly independent. Also fairly obvious. And then the third one, if if v1, that's fine. If v1 is not a scalar multiple of v2, then the set consisting of v1 and v2 is linearly independent. So these are nice facts to hold on to. This one's pretty obvious. There's no point in putting the 0 vector into a set if we want to talk about linearly independent. A single vector is always linearly independent as long as it's not the 0 vector. Also, and this is a nice way to check for linear independence when you have a set consisting of 2 vectors. As long as one of them is not a multiple of the other, then that set is linearly independent. Now, I want to get a feeling for, so we've got this definition, and it's purely computational in nature, right, the definition. But linear independence has a geometric flavor to it also. And so the way you want to think of linear independence, right, if you write down this set V1 up through VK, what it means, and I'm just going to put this in quotes for now, and we'll make this precise. This set right here is linearly independent if there's no redundant vectors. I guess I'll do the air quotes, I guess. So linear independence means no redundant vectors, and linearly dependent means that there's a redundant vector. And so let me say exactly what I mean by redundant. or I'll try to show what I mean by that. So first, so let's say, let's write this like this: interpretation of linear independence. Now, this interpretation that I'm about to develop right here is actually the definition that's given in the book. Okay, so I went about it different from the way the book goes. I gave you the precise definition, and now the interpretation is what we're going to find next. So suppose that our equation a1 times v1 plus a2 times v2 plus dot 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 plus a sub k times v sub k equals the zero vector has a non-trivial solution. So what we're saying right here is that suppose the set v1 up through v sub k is linearly dependent. Okay, so what does that mean? That means that there is a way to solve this equation where at least one of those AIs is not equal to 0. So then, at least, well, let's just say that, so then a sub I is not equal to 0 for some I between 1 and k. Now, it might be a whole bunch of them that are not equal to 0, but at least one of them, and let's call it a sub I, is non-zero. So now, a sub I times v sub I is equal to negative a1 v1 minus a2 v2 minus dot 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 minus let's see, so there'll be an ai minus 1 v. I'm gonna run out of room. Okay, I need to compactify my notation here. So what I'm doing, I'm taking this equation right here, I'm focusing on the a sub I, v sub I, and I'm subtracting all the other stuff over to the right-hand side of the equation. But I need to save some room here. Dot, 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 minus a sub I minus 1, v sub I minus 1, minus a sub I plus 1, v sub I plus 1, minus dot, 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 minus v, a k v sub k. Sorry, I went a little bit quick there, but the idea is take this equation, subtract all the stuff over to the right-hand side except a sub I times v sub I. And now we can solve for v sub I. So v sub I, because a sub I is non-zero, I can divide both sides of the equation by a sub I, and what we get is minus a1 over over ai times v1 minus dot 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 minus a I minus 1 over ai vi minus 1 minus ai plus 1 vi plus 1, that's over ai, and then minus dot 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 minus ak over ai times v sub k. So what we have right here, we've expressed v sub I as a linear combination of all the other vectors. So let's say it like this then. It follows that a sub I is in the span of all the other vectors. So that would be v1 up through vi minus 1, vi plus 1, dot, 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 vk. That, not ai, sorry, that should say vi right there. So this captures this idea of redundancy in the situation where we have a linearly dependent set. one of the vectors will lie in the span of all the others. And so in some sense, we don't need that vector. And we'll see what we mean by needing later on. So in fact, I want to write this down as a theorem now. The set V1 up through Vk is linearly dependent if and only if one of the vectors lies in the span of the rest. So when I talk about redundancy, what it's saying is that in terms of spanning sets, we didn't need the V sub I. It's redundant. And there's also a nice geometric picture when it comes to linear dependence versus independence. So here's a picture of linear independence versus dependence. So notice V1 and V2, the span of those two vectors is a plane, and now I'm going to put a V3 up here. This is an example, a picture of linear independence. No one of those vectors lies in the span of the other two. That's what linear independence looks like. Here, I can only draw it in the three-dimensional picture, or in the three-dimensional setting. Compared with, so let me draw a picture now of linear dependence. So I start off, here's my V1, here's my V2. And if I draw a third vector, V3, sitting inside that plane, inside the span of V1, V2, this is what linear dependence looks like. V3 lies in the span of V1 and V2. Okay, so now suppose let's call them V1 up through Vm. So V1 up through Vm are in Rn, where in this case I want m to be strictly greater than n. And I want to write out each of these v's. So if we write v sub I equal to, so it's a column vector, v sub I, and I'm going to put the I in the first subscript, so it'll be a vi1, vi2 dot 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 down to vin. And once I do this, I can consider the equation. So let's say, and consider the equation a1 times v1 plus dot 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 plus a m vm equals the zero vector. Now, the corresponding augmented matrix is going to look like this. So we're going to have zeros over here. We're going to have vi1 all the way to vim. Oh, no. Sorry, this would be v11, and this would be vn. Who would it be? This is the vi. Oh, this would be v1m. This would be v21 up through v2m. And we go down here, we're going to have a n1, v2, nm. Right, okay, so what do we have here? If we look at the coefficient matrix corresponding to this system right here, what we should notice is that there are more columns than there are rows, right? There are m columns and there are n rows. All right, in such a system, what do we know? There's at least one free variable. So this system has, depending on what m is, there's at least one free variable. There might be more. So this system has a free variable. And what does that tell us? It tells us actually that it has an infinite number of solutions. In particular, it has non-trivial solutions. So the system has non-trivial solutions. So what does that tell us then? It tells us that this set right here is linearly dependent. So let's write this down as a theorem. Suppose V1 up through Vm is a subset of Rn. If m is greater than n, then our set V1 up through Vm is linearly dependent. Okay, so what this allows us to do then is to identify linearly dependence or linear dependence in certain situations just by counting, right? If you have m column vectors and that number m is greater than n, then you're guaranteed the set is linearly dependent. This does not go the other way. Just because if m is smaller than n, it does not guarantee that you have a linearly independent set though, right? So you can only use this theorem as stated right there. Okay, so that's it for now. Linear independence is going to come up constantly just as this concept of span, right? So I had a hard time with both span and linear independence when I was learning this stuff. It took a while to sink in. So hopefully by practicing this and you know, sort of emphasizing what's going on with linear independence, it will sink in for you quicker than it did for me. Okay, so we'll see you next time. All right, bye.